Welcome to Brain Vision.
Okay, so we're doing chapter 37, problem 80 here. So it says, by what potential difference must a proton or an electron be accelerated to have a wavelength of 6 times 10 to the negative 12 meters? Okay, so we can use the de Broglie's relation in equation 37.7 to know that the momentum is written by h over lambda. So that means to get a lambda of 6 times 10 to the negative 12 meters, we can figure out what momentums we need. So this is 6.63 times 10 to the negative 34 joule seconds over 6 times 10 to the negative 12 meters. So this becomes a momentum of 1.11 times 10 to the 22 kilogram meters per second. So this is the momentum we need to accelerate our proton or electron to. Okay, so for the proton, we can use the classical definition of momentum to determine the speed. And from that, we know that the speed is just the momentum over the mass. So this is 1.11 times 10 to the 22 kilogram meters per second over 1.67 times 10 to the negative 27 kilograms. So this comes out to being 6.65 times 10 to the 4 meters per second. And this is much, much less than c, so we can confirm that our classical approximation is probably valid here. Now we know that all of the potential energy is going to be converted to kinetic energy as we accelerate here. So the potential energy is given by EV, and this needs to be equal to the kinetic energy, which is given by mv squared over 2. So then if we're looking for the potential difference, delta V here, and put a delta, this is just given by mv squared over 2e. Okay, so let's plug this in. 1.67 times 10 to the negative 27 kilograms times 6.65 times 10 to the 4 meters per second, and then this is squared, all over 2 times 1.6 times 10 to the negative 19 coulombs. Cool. So everything's in SI units, so let's plug this in, and we get a potential difference of 23 volts. Cool. Okay, so this was part A for a proton. Let me write that out, proton. Okay, so let's do part B now for an electron. So for the electron, if we divide the momentum by the electron mass, we're going to obtain a speed that is greater than 10% of the speed of light. So now we already know that we're going to need to use our relativistic equations. So first we can know that the energy can be written here as this p squared c squared plus m squared c to the 4th, and then all square rooted. So if we want to find the energy here, let's go ahead and plug things in. So this is momentum here, 1.11 times 10 to the negative 22 squared times 3 times 10 to the 8 for C squared plus 9.11 times 10 to the negative 31 kilograms is the mass squared, and then 3 times 10 to the 8 meters per second to the 4th. And then we're going to square root all of this. Okay, so if we plug all that in, we get an energy of our electron being 8.85 times 10 to the negative 14 joules. So if this is the total energy, we need to find the kinetic energy first, because we know we can use this relation we have up here only if we have the kinetic energy. So if this is the total energy, then the kinetic energy is just E minus the rest energy. So let's do that. So this is 8.85 times 10 to the negative 14 joules minus 9.11 times 10 to the negative 31 times 3 times 10 to the 8th, and then this is squared. Okay, so if we plug that in, we get a kinetic energy of 6.5 times 10 to the negative 15 joules. And now from the kinetic energy, let's go over here, and we know that delta V is K over E. So this is just 6.5 times 10 to the negative 15 joules over 1.6 times 10 to the negative 19 coulombs. And delta V comes out to being, when we plug this in, 41,000, I'm rounding here, 41,000 volts or 41 kilovolts. Cool. So it takes a lot more potential difference to get the same de Broglie wavelength out of accelerating an electron rather than a